Farkas from Berlin, speaking about moduli of K3 surfaces via cubic fourfolds.
Yeah, so thank you very much for this opportunity to speak in your seminar. So I will talk about a way of parameterizing moduli of K3 surfaces via cubic fourfolds, and I expect that in using a correspondence between cubic surfaces, K3 surface and cubic fourfolds, that I expect it's sort of familiar to a lot of people in this seminar. Right, so let me just start with the moduli space itself. So I will denote the moduli space of K3 surfaces by Fg. This is the Mukai notation, and it is the parameter space of pairs S, H, where S is a K3 surface, and H is a polarization, so an ample, or if you wish, globally generated line bundle of self-degree of self-intersection 2G minus 2. Yeah, so this is the degree, but I prefer to call it a K3 surface of genus G, in the sense that the hyperplane sections of these K3 surfaces are canonical curves of genus G. So one knows that this is a very prominent moduli space in algebraic geometry. Via Torelli's theorem and via Hodge theory, you can show that this is an irreducible 19-dimensional variety. Yeah. Okay, and right, so this has been studied a lot, and I would just a couple of pointers here. So first of all, there is a fundamental result of Gritsenko-Hulek-Sankaran, where they used work of Borchers and automorphic techniques to show that this moduli space is of general type when G is sufficiently large. Essentially, I should say G greater than 46, and there are a few exceptions, which I don't want to discuss. But in these cases, you expect definitely the result to be the same. And on the other hand, there is work, so this is some sort of negative result, if you wish. There is work, very well-known work of Mukai from the 80s and 90s, where for a small genus, so let's say to start with genus less than 10, he produced really wonderful structured theorems for K3 surfaces of small genus. So he produced a variety VG. Well, I could call it MG, but that Mukai variety, but that would be, I don't want to call anything MG other than MG itself. So this is called the Mukai variety. So this is a rational homogeneous variety embedded in a projective space of dimension NG plus G minus 2. So the dimension of this is NG. And this is a Fano variety. And it has index 2 minus NG. So this is O of 2 minus NG. So this is already embedded. And right. Okay, 2 minus NG. And it has the following property that if you start to take two-dimensional linear sections of this variety, so you look at two-dimensional linear sections, of VG. So how do you get this? So you look at this variety, yeah, so it is embedded in this projective space, and you intersect it, you cut it with co-dimension with NG minus 2 planes, so you end up in P to the G, and by the adjunction formula, these will be Calabi-Yau varieties, and you can see the fact that they will be K3 surfaces. And Mukai is telling you, in fact, that you are going to get all the K3 surfaces. Well, I put here one-to-one, more or less, K3 surfaces of genus G. And this, of course, you have to mod out here by the automorphism of this VG. And this is a tremendously useful theorem because it offers a realization of the moduli space in terms of extremely concrete terms. So this is really one-to-one is birational, right? But you know more exactly what K3 surfaces do not appear in this way and so on. So it implies that in this range, yeah, so the parameter space of such a linear section, so this is just a Grassmannian of G-dimensional planes in this space ng plus g minus 2, modulo this automorphism group, is isomorphic birationally to Fg. Yeah, so it's quite a remarkable fact, and it is extremely useful, and it has been used countlessly many times in various contexts. And to give an example of this, how this works, right, so one consequence of this, a consequence of this, of course, is that the moduli space is unirational in this range. But you know much more than that. You have really a recipe of realizing K3 surfaces for small genus actually over any field. So let's give an example to see how this works. It's the case genus 8. So for genus 8, so this is a theorem that you can prove it case by case. And Mukai actually has pretty much for each case, each genus you has a different paper. So V8 is the Grassmannian G26. So this is the same thing as the Grassmannian of lines in P5. Now, via the Plucare embedding, this is embedded in P14. And you see that N8 in this case is 2 times 4, so 8. And so this condition is satisfied because the Grassmannian in the Plucare embedding has index 6. And what the theorem says, it says that, well, I take the Grassmannian of projective 8 planes in this P14, and I mod out by the automorphism of the Grassmannian, which is PGL6. This is birationally isomorphic to F8. And let's count dimensions for some safety check. So this is like G915. So this is a 54. And the dimension of PGL, this is 35, PGL6, 35. And here you have 19. So at least the dimensions are the same. And so this is, as I say, kind of a summary of Mukai's work for genus less than 10. And of course, Mukai did not stop here. So he went on. And for genus, well, genus 11 is a special story. This is in some sense the most exotic case. This is, let's call it the exotic case, but it's very beautiful and very well understood. And then for genus 12, 13, 16, 17, 18, and 20, Mukai has similar structure results, which I don't want to describe. Some are better known, some are less well known. Less well known, so has similar results, in the sense that the K3 surface can be obtained as after a recipe as sections of with respect to some vector bundles over some rational homogeneous varieties over Hilbert schemes of some curves and so on. So in any case, it follows in all these cases that Fg is unirational.
Can I ask about the V8? So this is intersection of 3 quadrics in P5, right?
Yeah, yeah.
And why is it Grassmannian 2,6?
No, this sorry, which one? Genus.
So V8. It's genus 8. Sorry, I thought
genus 8. So this is D equals 14.
Yeah. Thanks. Thank you.
So sorry. Yeah. This is the right. I am with the genus always, not with the the degree. Right. Okay. So. Good. So right. So this is the situation, right. So there is a lot, of course, very interesting questions related to these models, and what we are going to discuss is, well. So you see that somehow the first genus that is missing in this list is genus 14. This is not in Mukai's list, and this is we will be covered in this work with Sandro Verra, and and actually I just learned, in fact, from Claire recently that apparently genus 15 somebody can handle genus 15 using this de Bar-Voisin variety, hyperkähler varieties, which is interesting, but I don't know anything about this work. Okay, so right, so this is the summary of what we want to do. Any questions? Okay, so then I continue with cubic fourfolds. Right, so cubic fourfolds. Yeah, so let me start by recalling a couple of basic things. So you start, so cubic fourfolds form a moduli space of very simple moduli space of dimension 20. So this is the moduli space of cubic fourfolds in P5, right? Modulo PGL6. So this is a 20-dimensional moduli space. And one thing, well, there is, of course, a lot of questions and work on rationality of cubic fourfolds, and I don't want to go into that. So the point is that you can look at the two-dimensional cycles on cubic fourfolds, and for cubic fourfolds, it is known due to work of Voisin that the group of the second Chow group is isomorphic to H22, the integral H22. And if you start to look at the numbers here, the numbers in the Hodge diamond, you get the following numbers: 0, 1, 20, 1, 0. And then you look at this one in the middle, and you immediately will recognize, well, that these are the numbers that appear in H2 of a K3 surface. And of course, you can ask whether, well, is this an isomorphism of Hodge structures? And this looks like the H2 of a K3 surface, but the signatures are different. So the signatures are different. So the signature in this case is 220 for a cubic fourfold, for a cubic fourfold. And it is 319 for a K3. But this fact leaves open the possibility of the two objects, the mysterious K3 and the cubic fourfold, of having a common codimension 1 Hodge structure that appears in both, right? So maybe there is a codimension 2 such Hodge structure that is of signature. So maybe of signature necessarily then of signature 219. So this is a Hodge structure common to both. Okay, maybe. And of course, for that, well, you know that if X is generic in C20, then this is just CH2 is just one-dimensional. So then there is no hope for anything. It's just complete intersections. But so you have to if you want to make progress here, you have to allow a neutral-Lesher special cubic fourfolds. And then for a degree D, for a discriminant D, you denote. So following now, I'm kind of reviewing the PhD thesis of Brendan Hassett. You look at the space of those cubic fourfolds which admit a cycle that is not a complete intersection. So there exists an embedding of this rank 2 lattice in CH2. And this is of discriminant D. So alpha is some cycle, discriminant D. And right, and well, it's known that CD is non-empty, and if it's non-empty, then it's an irreducible divisor. If D is congruent to 0 or 2 mod 6, and D is greater than 6, strictly greater than 6, and in these cases, this is an irreducible divisor if non-empty. And then you have so this neutral-Lesher locus is the union of countably many neutral-Lesher divisors. And you can ask, we were after this K3 surface, so you can say now that the cubic fourfold, so again, this is all due to Hassett, X has an associated K3 surface. If what I just said can be actually realized. If there exists a K3 surface, if there exists an S K3, with the property that when I take the orthogonal of this codimension 2 lattice, I ran over the H2 of this K3.
So there's a question in the chat about 20. So it's 21, right? For the cubic.
Yes. No.
Because you take orthogonal of 2 classes.
Sorry. I take the primitive one. Yeah. Right. So I'm sorry. This is fine. I of course.
But primitive one for K3 would give us number 19.
Yes, we are going to get there. But I made a mistake here, and I would like to correct this. Yeah. First of all, thank you. This is right. You take the primitive, of course. Right. So and I have not this because now I take the primitive here as well. Right. Okay. So if this is realized, then you say that you have an associated K3 surface, and this is just an isomorphism of Hodge structure. So the K3 surface here is not really explicit in any way, and this has also been discussed by Hassett in this thesis, and this happens precisely if this discriminant is an Eisenstein integer. if D has the following bizarre properties, D is not divisible by 4, 9, or any prime congruent to 2 mod 3, by 4, 9, or any P prime congruent to 2 mod 3. Yes, okay. And so there is some numbers with these properties. So they are 8, and then 14, and then 26, then 38, and then 42, and so on. Yeah, so 8 is in some sense a fake case. All right, so this is still not a very, for my taste, is still pretty mysterious definition, because I would like something more geometric, and then we get to, so in this, you look at these papers of Hesseth and Eddington and others, there is this condition, star, double star, triple star, and so on. And this is what I'm explaining right now. If you have, of course, there is a way of making this more precise. If you have your X, the cubic fourfold, you can associate the associated hyperkähler Fano variety of lines on it, right? So this is line, this is L in G15, so lines in P5 that happens to lie on my X. So this is a hyperkähler fourfold. And of course, I have a K3 surface. I have an obvious hyperkähler fourfold, the symmetric square of the K3 surface. And you can ask, when is this? So this condition here, when can we make it more precise? Namely, that the associated, the Boville-Donaghy fourfold is isomorphic to the Hilbert square of the K3 surface. And this happens, it turns out, this is all Hesseth, that this happens if D is of the following form, 2 times n squared, and this is now D is 2g minus 2. N squared plus n plus 1, where n is greater than or equal to 2. So this is the condition that will be all important in this talk. So the case n equals 2 that leads to D equals 14 genus 8. This is the famous case of Fano and Morin, right? So there was a famous incorrect proof that all the cubic fourfolds are rational, and it was exactly this case. And then the case, so D n equals 2 is this Fano-Morin case. This is classical. People recently, like Russo and Bolognesi, have revisited this. Then the case n equals 3 is done in, this is D equals 26, so genus 14. This is handled in one of our papers with Sandro, and n equals 4 is D equals 42, and this is handled in another paper. And there is also work, interesting works of, okay, this is our paper, but there is also interesting work which is quite related to of Lai. And right, in this story. Okay, so I should say something about this case of Hesseth, right? So in this case, we have in fact a map between 2 moduli spaces, right? So there is a map between 2 moduli spaces, and this is the moduli space FD over 2 plus 1 into CD, right? Then which is associated to a K3 surface, so polarized K3 surface is associates the cubic fourfold, the associated cubic fourfold, and this is with this property, yes, such that S2 is isomorphic to Fx. And this is a morph is a map between moduli spaces given at the level of Hodge structures, and we know also that this map, the degree of this map is 1, so this is a birational map if D is congruent to 0 mod 6, and it's 2 if D is congruent to 2 mod 6. So depending on these properties, you have either 1 or 2 associated K3 surfaces to a cubic fourfold, and in fact we will appear, both cases will appear for 26 and 42, because you see that the 26 is congruent, well, 2 mod 6 and 42 divisible by 6. Okay. So right, so of course this has been used, right? So these type of constructions for rationality questions, but I think this is a very strong tool for studying this largely mysterious moduli space of K3 surfaces, and it should be more made out of it. Okay, so maybe now I summarize the results here. Yes, if you have any questions, please don't hesitate to interrupt me. So I will introduce the following notation. So I will call by FGN or FG1. Actually, I only need FG1, the universal K3 surface of genus G. So this is the universal K3 surface of genus G. So this is a 21-dimensional variety. And right, so it comes with a universal family over FG in the sense of stacks. And then we have two theorems, both joined with Sandro Verra. And they are 3 years apart. So the first one is that F14.1 is rational. And of course, this implies that F14 is uni-rational, at the very least. And F22.1 is uni-rational, which implies that F22 is uni-rational. And right, so then I should say that this is the highest genus for which is known that FG is not of general type. So remark, G equals 22 is the highest G for which is known, it is known, FG is known not to be of general type, is known for the time being. But perhaps more than the result is the method is sort of interesting, and it actually gives some hints of how to study these moduli spaces in general for for the higher values of G. Okay, so now how shall I right, so the strategy is the following. Maybe I will describe now the strategy here to understand these moduli spaces. So the strategy is to take this Hesset isomorphism and to get out of it, to make it as geometric as possible, make a concrete question about some moduli space of curves, and then solve it. So we have these two, I have two cases. So I have genus. So first of all, I have the case when genus is 14. And in this case, we have this moduli space from F14 to C26. And this is 1-to-1 birationally. And then I have the other case where I have it's 2-to-1. So in this case, it looks rather mysterious that a K3 surface of a cubic fourfold of discriminant 42 has two associated K3 surfaces. And
you can explain how the numeric works. Why is 14 and 26 and 22 and 42?
So again, D is 2G minus 2 always.
Oh yeah, thanks.
So
sorry.
you see, so
sorry.
I'm sorry. Yeah. So if I wrote like many people in the community here, the moduli space of polarized K3 surface of degree D by MD, then I would have D to D on both sides. But this is to just, I'm sorry, but it's this very simple transformation. D equals 2G minus 2. Yeah. Okay. Right. So what is so recall that we have this isomorphism between Fx and S2. And a priori, we don't know much about S, how to get S out of X. And the point is that, so of course, this is embedded in the Plucare space. Fx has an embedded in the Plucare space. And we know this has been observed before, what is actually, it appears even in the paper of Bovil and Donaghy, what is this OS2 of 1? Yes, so this is the Plucare bundle at the level of the Hilbert square, and this is equal to it's equal to 2 times F minus 2F minus 7 times delta if D is if G is 14, and it's 2F minus 9 delta if G is 26. Right. So here delta is the class of the diagonal, the reduced class of the diagonal. So this is the diagonal. So these are the cycles which are non-reduced, if you want, and delta is the class of it, but 1/2 of it, right? So delta is 1/2 the class of the diagonal, and F is the polarization class on the Hilbert square. So F is the class of cycles of type right. So I have here Xi saying S2 with a property that Xi intersects a given curve where C is a fixed curve in the polarization class. C0 maybe fixed. So we have these formulas which are right, and it will turn out. So what I am going to do now is I'm going to turn this problem into essentially canonical into a problem about scrolls. And so how are you going to get your hands on the K3 surface using this isomorphism alone? Well, you start with a point on your K3 surface. A priori, you don't know anything about this K3 surface. Then of course, this delta is a P1 bundle over the K3 surface itself. So you can associate to P the space of those cycles, two cycles that elements in S2, which are supported on P. So this is, of course, a P1. So this is a rational curve. So to each point of the K3 surface, you view it as a rational curve in S2. But now if I use this isomorphism between S2 and Fx, I get a rational curve in Fx. But a rational curve in Fx is a line of lines, a rational curve of lines. So this is what is called in classical algebraic geometry a scroll, per definition. This is the scroll. And of course, it's a scroll inside X. So it's a scroll. It's a two-dimensional scroll inside X, and it is associated. So in some sense, more or less tautologically, in this case, the K3 surface is a Hilbert scheme of scrolls. And what is the degree of the scroll? Well, the degree of the scroll can be read from this formula. So the degree of the scroll is 7 in the case G equals 14, and it's 9 in the case G equals 26. And now, well, so it turns out, right, so we can actually compute this lattice in each case, right? So we can look at the lattice here. So I have here H squared, I have this scroll R is RP, and so look at the numbers here are, so here this is 3, and then I have there, if they are septic scrolls, then I want to have the discriminant should be now 26. So this is 25 in one case, and in the other case, you compute, and then I have this 3. Now these are nonic scrolls, so they are not septimic scrolls. I learned this is the correct way to say it. And I want the discriminant to be 42, so this should be 41. So you can compute the self-intersection, and if you have the self-intersection, there is something called the double point formula. You can look it up in Fulton's book. And if assuming this scroll has simpler singularities, so non-normal nodes, then it turns out that the number of nodes is so these are non-normal nodes, or classically called the parent double points. This is equal to 3 if D is equal to if G is equal to 14, and 8 if G is equal to 22. So these scrolls cannot be smooth. They will have nodes, and you don't expect a scroll, a two-dimensional surface in something in a surface in cubic fourfold to be smooth, and this is the number of nodes. And of course, you can do this for the other values of the in this Hassett numerology, but the numbers will become harder and harder. I mean, the number of nodes and the degree will become larger. So to summarize this, if we want to study this now, we can, if we want to study so C26, we are led to septimic scrolls, degree 7 scrolls with 3 nodes. And if you want to study C42, so now I have you are looking at nonic scrolls, degree 9 scrolls with 8 nodes. Okay. And now at this moment, I will leave this degree 14, and I will concentrate on the highest degree genus for which we can do this, and this is degree 42. Okay, so right. So to summarize here, as what I said so far is that you can realize these scrolls as this K3 surface is some sort of Hilbert scheme of curves. Of course, this is of scrolls, but this is of course not a particularly concrete incarnation. So the next thing I would like to set up an incidence correspondence. So this is pretty clear, and this has been also appears in the work of Lai, the incidence correspondence, and also in our first paper, between scrolls and K3 surfaces. So this is an obvious thing to do. And this will lead exactly to this universal K3 surface. So we are in either case, but let's say we focus from now on this case alone. So then we look at this parameter space which parameterizes pairs R and X, where R in X in P5. So this is a cubic, and this is a scroll. And it's a scroll of this degree with this number of nodes, right? So in degree 42, in degree 9 and 8 nodes. And I mod this out by PGL 6 here. And then, of course, this comes endowed with 2 projections. So here I have, first of all, the second projection. This is the map to F. So I'm in genus 22. Genus 22. So this is this goes to C42. Yeah, and then I have a map to a Hilbert scheme of scrolls. So this is a moduli space of scrolls. So this is the moduli space of scrolls. And this is pi1. And the fibers of pi2, by what I described here, the fibers are the K3 surfaces itself, right? So in this case, it turns out that this is the yeah. So let me make a little theorem here, or maybe proposition. Theorem is too much to say, that we had this ambiguity. Recall that we have this ambiguity. So from F22 to C42, and this is a 2-to-1 map, right? And if we lift this ambiguity, if you pass to the universal K3 surface defined as this incidence correspondence, then this ambiguity disappears. So X is birationally isomorphic. Birationally isomorphic to the universal K3 surface. To the universal K3 surface. F22. So in the sense that I have this 2-to-1 map here, this is this 2-to-1 map, and then this becomes really the universal K3. And this is really not such a difficult thing to understand, because it just means that that there are 2 types of scrolls here in each cubic fourfold, and they can be understood actually numerically. It's a solution of certain Pell equation. Okay, and the next thing I want to say is that, well, the fibers of pi1 are not mysterious at all. So the map from X to pi1 is a projective bundle. So it's a to this moduli space of scroll. So this is a projective bundle. Because what is the fiber? I take a scroll, such a scroll here. So what is then the fiber of this? The fiber of over this scroll is just the projectivization of the space of cubics containing this scroll. So this is just a vector space. And the dimension can be computed. So for instance, I can explain how this works, right? So if you assume that R has exactly 8 nodes, so the singularity of R is exactly 8 nodes, then of course you have this, you have here A0 of IR3. Then you look at A0 of I, then comes here the singularity in P5 of 3. And then I have here the obvious thing, what is here, H over R of 3. And well, you can find such a scroll. You can show that you can find such a scroll for which this map is surjective here, right? So this will be 8 choose 3 minus 8, right? So this is 56 minus 8, so this is 48. And well, so now you have to know something a little bit about scrolls of degree 10, or degree 9 rather, right? So if you look in algebraic geometry 101, so scrolls of degree 9, first of all, you look at those that are smooth scrolls, right? So they will live in P10. And so you look at the Hirzebruch surface F1, which is just the blow up of P2 at one point, and you embed this in P10, by taking the linear system 5h minus 4 times e. Yes, and the image here, so the image is a smooth scroll in P10 of degree 25 minus 16 on degree 9. And this is a smooth scroll. And the point is now that how do you get a scroll with 8 nodes? Well, you will project. So to get a scroll in P5 with 8 nodes, you will project to P5, and you will make this projection from the center of this projection. So this is here, the smooth guy will be here, and the nodal guy will be down here. And the image of so you choose a gamma, a 4 plane. That is, so you have to have a secant to the secant variety. So how many sequencing conditions you impose? It's exactly the number of singularities, which is 8 secant to the secant variety of R prime. So of course the secant variety of R prime is known, right? So this is in P10, has determinantal equations, and then R is just the image of this. And in fact, any such scroll will appear in this way. And this is now 8 nodal non-scroll. Yeah, any questions to this? All right, so then of course you can now understand this. You can now compute what is this number here, right? And this is, you look at, so you see we are O of 1, so I have here O of 3, but O of 1 is 5h minus 4e. So this is the linear system 15h minus 12 times e minus, and you want to have 8 nodes, right? So minus the sum from 1 to 8 of 2 points. These are the inverse images of the nodes. Okay, and if I compute these numbers correctly, so I should get here. So all right, so this is 42 anyway. This is 42 dimensional, and so this one here should be 5 dimensional, 6 dimensional. But when I projectivize, it's going to be 5 dimensional. So this is a P5 bundle. Of course, there is something to prove here, and this can be done in various ways. For instance, just writing down one example where all I said here, and you can do this with computer algebra, all I said here is holds, right? And all these dimensions are like this, and this map is also surjective. And then it shows that this universal K3 surface is in fact a P5 bundle over this moduli space of scrolls in P5. And then the question of understanding modular K3 surfaces of genus 22 boils down to understanding these scrolls. So this is the moral. So by what I said here, these considerations, which are rather simple, are the uniruleness of the moduli space follows immediately, right? And we just have to discuss now the base. All right. Okay. So then I continue. And so maybe let's summarize this. So summary, the universal K3 surface, so F22(1), is a P5 bundle over a moduli space of scrolls. Over a moduli space H scroll of nonic scrolls with 8 nodes. Okay, and the dimension of this is, of course, then this is a 16-dimensional variety, and the rest is how to understand this. And in some sense, this is where our work with Sandro really starts. Okay, and right, so we would like to prove, we will prove at the end of the day that this moduli space H scroll, so this is the theorem with Verra, that this moduli space in fact is unirational, and it has a very nice parametrization. And in fact, then therefore F22(1) is unirational. Okay, so right, so let's start and explain this strategy. So start with such a scroll. So R is in P5. it's a scroll of degree 9, which has 8 nodes. And assume that the singularities are really non-normal nodes, right? So N1 up to N8. And now comes our fundamental observation here is the following. So I put here the N nodes, the 8 nodes. I have 8 nodes. And now, of course, the scroll has rulings as well. And I would like to choose also 4 rulings. 1, 2, 3, 4. So these are rulings, L1, L2, L3, L4. So these are rulings. And now I count here moduli. I look at the quadrics in P5. So this is a quadric. And the quadric depends on 20 moduli. So the dimension of linear system of quadrics in P5 is 20. P is P20, yeah? Okay, so now I have 8 nodes and 4 lines. And it just happens that 20 is equal to 3 times 4 plus 8. And if I impose on the quadrics the condition that these quadrics contain each of the nodes, that is 1 condition per node, and then I impose the condition that the quadric contain the line that is 3, so a quadric containing a line that is 3 conditions, then it means that if everything goes according to plan, there should be a unique quadric containing the N1, N8s, the nodes, as well as the 4 rulings. So we hope that there is a unique quadric in P5 containing N1 and 8, as well as L1, L4. And then I am led to introduce the following auxiliary moduli space. So this is a canonical P. I'm interested in this moduli space of scrolls, of course, but in fact, I will now define a P1 bundle, an M04 moduli space over it. So the fibers are M04s, and this is the moduli space, which I call, say by, so let's see P. So set P. This is the moduli space which parameterizes scrolls together with the unordered choice of 4 rulings. So Li in R are rulings. And of course, there is I mod out by the action of PGL6 here everywhere. And this will be, of course, will map onto the Hilbert scheme of scrolls. Or it's not Hilbert scheme, moduli space of scrolls, sorry. And the fibers are M04s, right? It's just the choice of taking 4 points in P1. And of course, this makes no difference whether I do it ordered or unordered. So this is a P1 bundle.
You want the lines to be disjoint from the singularities.
Right. Everything is birational. But thank you. I want the lines to be disjoint to the singularities. Yes. Right, exactly. Okay. So this is a 17-dimensional thing, variety. So this was 16-dimensional. Okay. And now the point is that when, right, so I can now summarize the discussion here that, so given so I had these nodes, yeah, N1, N8, and I had these rulings, L1, L4. Yes. So to R, I associate the unique quadric Q in P5 with these properties. And this quadric will cut now. This will not contain the scroll, of course. Yes, will not contain the scroll in general, but it will cut on the scroll the 4 lines, they are there, and something else. And this something else is a curve. And this is it's a scroll of degree 9. So this is degree 18, and I subtract 4. So this is a curve of degree 14. Degree of this is 14. So it's a curve of degree 14. And this is also, so it's a, and it has, of course, singularities at the nodes, at the N1, at the nodes of the scroll. So singular curve. So this is a curve that is singular at the 8 points. Okay. So this is in some sense once you you got the idea to look at this curve, then you are already on the way to the solution. Because then, so what type of curve is this? Well, so recall that I said that this is this scroll, the O of 1 on this scroll was this 5H minus, so recall how this scroll was obtained. You had the Hirzebruch surface and then you embedded it in P10 and then you project. Every scroll is obtained in this way. Yeah? So this is R and this is in P5. And now to have it, right? So what linear system will be here? So this is the linear system here will be, so this was 5H minus 4A. So this was 10H minus 8A, E, the exceptional divisor. And I subtract minus 4 times H minus E. These are the class over the line. So I'm left all in all with a linear system H 6 times H minus 4 times E. So summa summarum, this is, if I look at the normalization of this curve, so this is the normalization map. The normalization map. C is a hyperelliptic. C is a curve endowed with it has a plane model which is sextic and has a 4 nodes of singularity of order 4 at some point. So this is then a hyperelliptic curve of genus 4. Hyperelliptic curve of genus 4. Genus 4 because 4 is, you look here, you look at it's right, you just that's the genus. So I take here the genus of this is 5 choose 2, the genus of a smooth plane curve of degree 6, and then I put this condition minus yeah, so this is the yes, so minus 6, yeah, so this is 4. Okay, so you associate to the whole picture Hilbert's hyperelliptic curve of genus 4, and it has a node, and it's 8 nodal, right? So gamma is 8 nodal, and what I was saying now, basically, you can introduce another moduli space, and I call this moduli space the moduli space of such objects, right? So this is the moduli space I put here, HIP4. So this is the moduli space of well, it's really this curve, of course, it comes endowed with an embedding in a projective space of dimension 5, right? So this is the moduli space of pairs gamma and L, where gamma is 8 nodal hyperelliptic curve of genus 4. And L is this embedding of gamma in P5 of degree, so L is what I would call a G5 degree of this was 14. And we have a little result here that this moduli space P, this P1 bundle over the Hilbert scheme of scrolls. So this was P1. This is in fact isomorphic to the hyperelliptic, to this moduli space. So you have this diagram like this. The fact that this is isomorphic, basically what I'm saying here is that once you have the hyperelliptic curve, you will recover the scroll. And I hope that, so this is quite easy, in fact. So given, if I can reverse this construction, so given gamma in P5, hyperelliptic, one can recover the scroll. How? Well, you just take 2 points, conjugate points on the hyperelliptic curve, and take the line joining them, and you take the union. So this is the union over all x in gamma, and here I have the line joining x and iota of x in P5, and I close this. This will be a scroll.
So is it a 2-section of the scroll kind of?
Yes, yes, yes. You see this from the linear system. In fact, that's what it is, right? So everything is very concrete here from this.
Can I ask to go a little
Please.
bit back? I mean, why wasn't it possible to show directly that some of the choices of the projection from R prime to R is parameterized by something rational or unirational?
Well, this we couldn't do because you look at this. This is what do you need? You need for that. This we couldn't do even for the previous case. In fact, so you look at this. So these are the 8. Look at this. So these are these 8 secant 4 planes. So this is a kind of a rather complicated condition. That so you look at those. Yeah. So how would you set this up? So okay, you have the secant variety of R prime. This has pretty concrete equations. So this is a 5-dimensional thing. Variety, and then you look at in the Grassmannian of 4 planes, you look at those that are 8 secant to this. So this doesn't look to us, at least it didn't look simpler than what we are doing. So, but I'm not saying that it cannot, maybe it can be done, but certainly this is not how we solved the previous case, which was simpler, the degree 26. So genus 14 there, we also, so our nature was always to go to a moduli space of curves. And there, it was actually moduli space of curves of genus 8, and then use that to get back to our result. So, and here, what we have a similar situation, we look at the moduli space of hyperelliptic curves of genus 4 with 8 nodes. Other questions? All right, but I hope it is kind of plausible, at least now that, yeah, so giving this gamma and this hyperelliptic curve, you can basically get back to the scroll. And then, of course, you have also the rulings, and then you get back this moduli space. So, you know, you are left with this studying this moduli space of hyperelliptic curves now. And now, of course, there are no cubic fourfolds, there are no K3 surfaces, there are just curves, right? And so let's see how this goes further. So now, how about this moduli space heap 4? But in some sense, our proofs in these 2 cases are 2 papers and they're 3 years apart, and they are quite ideologically they are sort of similar. Yeah, that you start with cubic fourfolds and you get at some point a moduli space of curves. So right, so I start with a rational with such a hyperelliptic curve, and this is a hyperelliptic curve of degree 14. And then, right, and okay, so then of course this will have a genus. The arithmetic genus of this is 12, because the normalization was genus 4, and it has 8 nodes. And let's look at how many quadrics it contains. So I look at the multiplication map into A0 of omega of 2. Well, let's look at the number. So this is certainly 7 choose 2. This is 21. And this is 28 plus 1 minus 12. So this is 17. And well, actually, you can show that such curves are projectively normal. So there are 4 quadrics. So there are 4 quadrics, and there are 4 quadrics in P5 that contain this curve. So these are not the same quadric as the one we had before. And this will be gamma plus something else. And I call this the residual curve B, right? So this is 2 to 16. So this was degree 14. And now here we are in luck, because then this is of degree 2, and this is therefore a conic. And if it's a conic, then it spans a P2. And now you look at this. So now I will do some little projective geometry. Forgive me, please. Right. So I have now a 4-dimensional space of conics, and I have this P2. And there will be, in this 4-dimensional linear space, there will be a 3-dimensional subspace. There is a 3-dimensional subspace. Let's call it spanned by, let's say it's spanned by the first 3 of them, doesn't matter, which contain these 2 planes. This you can convince yourself quite easily. And let's look at this intersection now. I look at the intersection of these 3 quadrics. This contains these 2 planes, and it does contain then, of course, something else, a residual surface. And this will be a residual surface of degree 7 in P5. But this is now a very simple surface. certainly simpler than what we started before, what we had before of degree 7. So this is a surface that lies on 3 quadrics, surface of degree 7 in P5 that lies on 3 quadrics, with the property that these quadrics intersect along a 2 plane. And there is a classification of such surfaces. And it turns out that this T is then, well, is just the blow up of P2 at 9 points. And the embedding into P5 is given by the quartics passing through these 9 points. Yes, so there is a little bit of projective geometry here. So, but the T is really obtained from this residuation procedure. Okay, and well, so then basically what I'm saying is that this gamma, the curve I started with, lies on this T, on this surface, and it has therefore, and this T is as a quadric model, so it has, gamma has an optic model, so gamma has an octic plane model. An octic plane model. Well, and if it's octic, it has genus, the normalization has genus 4. So therefore it has 14, 8, so 21 minus, yeah, so it's octic, so 7 choose 2, so 21 minus 4, so 17 nodes. But these 17 nodes are distributed in 2. 8 plus 9 nodes, yeah? And the 9 nodes are the nodes that come from blowing up this T. These are the nodes of T, so to say, blowing up the 9 points of P2. And these 8 nodes are really the nodes of the hyperelliptic curve, so to say. And now, so we have essentially gamma has this plane model. And now, right, so the last thing, and also my time is almost up, so is now that this moduli space, in fact, is this moduli space hyperelliptic is, of course, is unirational. And so how you have to have a way now of parameterizing hyperelliptic, so octic plane models whose normalization is hyperelliptic, which has this, so it has always 17 nodes, but you treat them differently, the 8 and the 9. They are not treated democratically, you separate them. And how to do this is there is now a fairly clear construction. So you start with a cubic scroll. And this is the last piece of geometry, projective geometry I do. Start with Z in P4 rational cubic scroll. So this is just the image of the Hirzebruch surface by 2H minus exceptional divisor. And now you look at this parameter space. When I have here, I take 8 points on the cubic scroll. I take also a line, and I take a further curve. So T1 up to T8 are points on the cubic scroll. L is the line in G14. There's a line in P4. And C is a curve in the following linear system. It has this. It has to be hyperelliptic, so it will lead in this linear system. So I put here. Let me put it like this: X1, Y1, X8, Y8, and then I have here 6H minus 4E. Right. So the cubic scroll, of course, again, I said that this cubic scroll is obtained by the blow up of P2 at 1 point, and you map it via the 2H minus E into Z. So this is the image, and this is in P4. Yeah. So, right. So all these things are well known. And for instance, if you read the book of Joe Harris, Algebraic Geometry of First Course, right. So I look at this is this is a hyperelliptic curve of genus 4, which passes through these points. And what are these points? So these points are the points conjugate to, yeah, so I have to, so how am I going to think about pairs of points, unordered pairs of points? Well, I'm going to take simply the P2 spanned by Ti and L, and I will intersect it with Z. And this will be, so this is a P2 and this intersects, this is a cubic. So it will intersect in 3 points, and these 3 points are Ti, and then the residual points I call Xi and Yi, and I cannot distinguish between Xi and Yi. I cannot distinguish between them. Okay, so anyway, and you see now that you count here moduli, you see that there is exactly one-dimensional linear space for such curves. And I should say something here that this is obviously a rational, I mean, obviously, yeah, almost obviously rational variety, because it is a map over Z8 fiber product cross G14. This is, in fact, a P1 bundle. right? I take the 8 points. So this is, and I take the line. Then this determines these 2 other points. And then I have exactly one-dimensional linear system of such curves. And the point is now that, in fact, having this data, so this is a rational variety. This is a rational variety. This data actually determines also dominates the moduli space of hyperelliptic curves. And how does it do? This is the last thing I want to say, right? So I have this structure here. And because, of course, having this curve now, I just associate to this object, right? So to the Ti and L and C, I associate the projection of the curve. This is my Z. This is my curve gamma, right? And this will have, of course, 8 nodes. The 8 nodes are distinguished. The 8 nodes are the nodes corresponding to PL of Xi, which is the same thing as PL of Yi, because Xi and Yi are the inverse images of the nodes of gamma. And this is from 1 to 8. And plus 9 other nodes, which are there. But now we have this separation of the nodes. All right, so this is basically the end of the talk. So remember that we had this moduli space of hyperelliptic curves. This was this P1 bundle over the base of the universal K3 surfaces, K3 surface. And maybe with a bit of effort, you can even prove that this is rational because we didn't do any invariant theory here. But this is dominated by this incidence correspondence obtained from a single rational cubic scroll. And basically this proves the theorem. And right, so it says, as I said, for the other case for genus 14, it's kind of in some sense simpler, but also a little older. And there we essentially reduce everything to moduli space of curves of genus 8. So thank you very much for your attention.
Any questions?
Yeah, can I ask some questions? So can you emphasize the role of the 2 associated K3s in degree 42?
Oh, yes, right. Yes, I can. Right. So the point here is that where are the, so I go to the, right. I meant to say this and I forgot. So when we look at this thing here, right? So I said that this ambiguity disappears. And the point here is that we had, when we look at the so right, so what is the class of such a scroll, right? The class of such a scroll. So here these are the codimension 1 classes. These are the class, so this is the divisor classes, the polarization respectively of the diagonal, right? And then I have the class when I fix a point on the K3 surface, I have the class is delta P. So this is the class of this curve delta, capital delta P. And I have this curve FP where I intersect F with impose the condition that it passes through a point. And now there are 2 curves of degree 9 in the Plucare embeddings. One is, of course, with respect to this formula. One is, of course, FP. This has degree 9 manifestly. But there is another one, and this is by a Pell equation. And this is exactly, this Pell equation has exactly degree, the degree, and I forgot the numerology. I know I have it here, is 6 FP. So it's very bizarre, minus 55 delta P. Right? This is an effective curve in Hilbert 2S, and it has also degree 9, as you can immediately check. So I wish I knew what do these numbers mean geometrically, but this I don't.
In terms of scrolls, you said there are 2 types of scrolls, right?
Yes, there are 2 types. There are 2 types of scrolls when you pass to the. There are 2 types of scrolls, and you pass to this. Sorry. Yes, in this when you give you start with a cubic when you start with a cubic with a cubic fourfold. Yes, there are 2 types of scrolls, and they correspond. They have the. But when you take this double, this 2-to-1 cover, then this ambiguity disappears. And this is realized by observing the dispel equation, namely that you look at the one cycle in Hilbert 2S of degree 9. This has precisely two solutions. So I don't know this very, yes, I wish I had a more geometric answer to this, but there is a similar, in smaller genus, there are similar things which we don't understand. There are these automorphisms of Hilbert 2S, even in genus 11, I think there is one which I wish I could, so if I don't understand genus 11, this type of thing in genus 11, it's hard to imagine that genus 22.
I mean, in your situation, is f of x Hilbert 2 of two different K3s?
Exactly. Yeah, it is.
And so
this map is 2 to 1.
You wrote down is just the original one with respect to the other K3.
Correct. Yeah. Yeah. So these calculations are in a paper of Debar and Macri and maybe elsewhere, but we took them from there certainly.
And I mean, you mentioned in the Mukai models, you know exactly which K3s appear in there.
Yeah.
Can you do the same thing for the cubic fourfolds in your model?
Maybe, yeah, maybe. So the point is that, well, I think so. There is all right. So I could say here there is, when you look at these maps, right? Basically, you're asking. So certainly you can understand, for instance, the indeterminacy of this map, right? But there are all sorts of very interesting questions about the moduli space of K3 surfaces. For instance, these versions of Fulton conjecture on M0n is the Noether-Lefschetz cone, the effective cone, right? So this is true for the Picard group. There is a well-known result of Bergeron and many other authors, right? But for the effective cone is an open question, and perhaps one could study this at the level of the cubic fourfolds and obtain something more transparent. I don't know this. So the fact that this the Mukai for the moduli space of K3 surface of genus less than 10 is known which ones do not appear and which one do appear, that played an important role in the other case, or degree 26, where we actually carried out the Mukai. We had to carry out the Mukai program, so to say, on the boundary, because it was not really a smooth curve of genus A that appeared, but a singular curve. And then, yeah, you just had to. So this was quite useful. Yes, I should say something that kind of a lot related to the circle of ideas then has been used in two very nice papers of Russo-Stagliano, where they actually looked at the rationality of the individual objects in C26, respectively 42. And there was a geometric construction, which is kind of, well, in the end, these scrolls didn't quite work, but they were very close to that.
More questions?
There's a question in the chat about can one get canonical curves of genus 14 and 22 using these constructions?
Sure. Yes, you can, of course. So the point is that, right, so I have not described the other construction, 14, that is simpler in some sense. Yes, you can. What is missing even in degree, so degree 26, genus 40, is that we still do wish we had, so we have we don't really know more what is the K3 surface than the Hilbert scheme of scrolls. We do not have, so in this degree 14, genus 8. In the Morin-Fano case, there you have a very concrete realization of the K3 surface. This is missing in that sense in the for the higher genera. So in some sense, the case of genus 14 is not in the Mukai model, Mukai program. With this vector bundle method of Mukai, you cannot get it. Numerically, you simply cannot get it. So that's why you don't get it on Mukai's terms.
Any other questions?
Can I ask regarding the scrolls? So you recover associated K3 as moduli of scrolls on a cubic fourfold. So is this step completely general?
Yeah, this is completely general. Assuming
Yep.
assuming you have the transversality, right? It could be that at some point there will be no, you have a number from this double point formula, right? But you still have to produce at least once. So you have to produce two things. You have to produce one example of such a scroll which has exactly these singularities and no further singularities, and no worse singularities. And this is done usually with Macaulay or with computer algebra or with, I don't know, other techniques, but this is going to become harder and harder for. So the next case, we did not see how this could work, in fact. But assuming that, yeah, it's general.
Okay, any other questions? Well, if not, then let's thank Gabi again. Thanks very much.
Yeah, my pleasure.
Thanks.